ID number 127, are you there?
Yes, sir.
Okay. 128. 129.
Present, sir.
Okay. And ID number 130.
Yes, sir.
Okay. Okay, let's continue our discussion on subspaces. Right, so subspace is basically a subset of a vector space, which itself is a vector space. Just to recollect the definition. Here again, I'll emphasize this point that a subset on which the same binary operations that were defined on the larger set V. Okay, so remember this once again, that these two binary operations are the ones that are defined on the larger set V itself. Okay, with a subset, you can in principle come up with different definitions of the two binary operations, and then you can check whether W is a vector space with these two new operations or not. Even if it is, we will not call that W with those two different operations as a subspace. Okay? Please remember this point. Notations, so capitals will denote subspaces, small letters will denote vectors or elements of these sets. Okay, then we also saw this proposition where if we are trying to verify whether a subset W is a subspace of the given vector space V or not, we need to only check two things. Okay, that W is closed with respect to vector addition and that W is closed with respect to scalar multiplication. Okay, remember these are the two conditions on any non-empty subset. Is there any doubt here? Okay. So we are going to follow for a little while the same flow that we followed in the group theory module. Okay, so we had defined a group, then we defined a subgroup. We basically know that subgroups are analogous to subspaces. Once we have the concept of subgroup, right, given subgroups, we wanted to see how to generate more subgroups. Okay, so the same thing is going to come up here. So let's say we are given two different subspaces of the vector space V. How can we generate new subspaces from these two subspaces U and W? Okay, so of course, the first way to try and see if we can get a new subspace is just take the union. Okay, so the first question is the union of two subspaces a subspace or not? Would anybody try this? Is this going to be a subspace or not?
No, sir.
No. Why?
Because two line, if two line are individually subspace, but they both are not making subspace, the whole plane should be there.
Right. So if I take this example, right, so let V be R2. If I take two subspaces, we already know that any line passing through the origin is a subspace. So this is a subspace and this other line is also a subspace. Let's call them U and W. The union of these two lines is of course not a subspace, because if I take this point here and let's say this point here, if I try to add them, I'm going to get this point here, right? And that of course doesn't belong to the union of U and W. Okay, so this is a counter example, and therefore U union W will typically not be a subspace. So union is not a subspace. How about intersection? Is intersection of two subspaces going to be a subspace?
Yes.
Prove it.
The intersection will have the elements which are present in both the subspaces, and since and including the identity. So since U and V are already the subspaces, their intersection will also be.
Yeah. So a proof should be sort of more precise.
We
Right?
can show that closure, inverse, and identity can be will hold here because U and W are subspaces. Hence, we can show that if two elements belong in U intersection W, then they belong in U and W. And
Right.
its closure will be achieved in both of them together. Hence, it will be present in their intersection also.
Right. So let's say that V1, V2 belong to U intersection W. Right? We need to show that V1 plus V2 also belongs to U intersection W, right?
Yes, sir.
Right? Should belong to this. Show this. How do you show that? V1 belongs to U, V2 also belongs to U, right? Since it belongs to the intersection. So therefore, V1 plus V2 will belong to U because U is a subspace. Similarly, V1 belongs to W, V2 belongs to W. Therefore, V1 plus V2 also belongs to W, and which implies V1 plus V2 belongs to the intersection of U and W. Right? In the same way, I think I can leave it as an exercise to show that for every scalar in the field and for every vector, say V in U intersection W, a scalar multiplication with V also is in U intersection. The proof follows the same line of thought. Okay, so that implies U intersection W is a subspace V.
Sir, we can also think of it as sir, we can also think of it as follows now, that U and V are subspaces. That means that U and W are having the same structure as V.
Yes.
Means therefore all the elements that are common to both U and W will also be having the same structure as V, and therefore we can say that it is a
No, so by structure, do you mean that you
relations.
have this? No, agreed. So that is true, but you need to show that. So any subset of the vector space V also will have the same structure, right?
Yes, sir, but the elements that are required for the property should be satisfied that may not be there, right, sir?
Exactly. So closure is something that we need to worry about, right?
Yes, sir.
And that's exactly what we have just proved.
Yes, sir. Means having the same structure is not a sufficient condition, but we have
Yes.
yes.
That okay? Any other doubts?
Yes, sir. It is okay.
Okay. Anybody else? Do you have any doubts here? Okay, so we saw that out of these two ways, and these two ways are basically using set operations, right? Union and intersection. to generate new sets. And of course, as it so happens, intersection of two subspaces yields another subspace. In what other ways can we generate newer subspaces? As far as set operations are concerned, we are done, right? There is nothing else to look at. Okay. How about vector space operations? So again, think of this as an analogous scenario with that of subgroups. If I give you two subgroups H and K of a group G, what can you do with H and K in order to generate new subgroups? Right. There also, if you talk of set operations, we know H union K may not be a subgroup, whereas H intersection K will always be a subgroup. What else did we see? Right. Would HK be a subgroup of the group G? Many of you recall this. I give you two subgroups H and K of a group G. Would the subset HK also be a subgroup? This was a question, I think, in the second or third tutorial itself.
If group is abelian.
If the group is abelian, then we know that HK will also be a subgroup. How about this scenario? The vector space V, is it an abelian group?
Yes.
With respect to addition, it is. So then, how can we generate a new subgroup or a subspace in this space?
U plus V, U plus W.
U plus W, right? It's the same as H into K. It's just that in groups, the group operation was denoted by a dot, or we didn't even make a specific notation for it when we write HK. This case, H and K are replaced by U and W. Okay, so that is what is called sum of subspaces. Okay, in general, so instead of limiting ourselves to only two subgroups or two subspaces, U1, let us U1 and U2, let us talk about the general case where we are given n subspaces. Okay, U1 to UN. And once we have a subspace, remember, we need not worry about scalar multiplication closure. Right? By definition, it is closed. Okay.
Sir,
So,
can we also
yes.
apply the concept of cosets like this?
Once again,
can we also extend the concepts of cosets in here?
yes. And if you remember, I had given a question in one of the tutorials where the group under consideration was R2 and a line passing through the origin was its subgroup. Does anybody recollect that example? I don't know. But that line passing through the origin is essentially a subspace of R2, right? And then, since it is also a subgroup, you can definitely talk about its cosets. Do you recall that example? Anyone? If you don't, please look at the tutorial. I don't remember which one was it. 3, 4, 5, or 6. One of these tutorials. I think the group was R2. We had given a subgroup which was a line passing through the origin, and we asked you to figure out what are the cosets. Okay, so instead of thinking of the line as a subgroup, you can think of it as a subspace as well. Okay, so the same concepts apply here as well. Right, so let's get back to this concept of sum of subspaces. If I have given you n subspaces of the same vector space V, the sum of these n subspaces is defined in this way, right? And this is again analogous to U1, U2 to UN in groups. All right, U1, so on and so forth, plus capital UN is defined as for every element in the n subspaces, you add them. Okay, and since all these elements are from the corresponding subspaces, which are subsets of V, of course, all these elements over here will be elements of the vector space V, surely. Okay, so you have these as your, this as your new set. Okay, so please remember again, we are just defining what is the set on the left hand side. Is it clear? Any doubts with the definition? Okay, so in that case, what remains to show is that the sum of these n subspaces, which is defined above, must also be a subspace of the vector space V. All right. How do you show this? So there are three things, right? One, is this set empty?
No, because U1 is not empty.
Right. So none of them are empty, right? U1 to UN. These are subspaces by definition. These are not empty, and which means they will at least have the additive identity in them, right? In all n of them. Okay. So since theta belongs to each and every ui, right? So theta plus theta, so on and so forth, plus theta, which is of course also theta. This belongs to this sum. Okay, so therefore, this is not empty. Okay, so that's the first thing. Then is the second thing, closure with respect to addition. Can I leave this as a homework? I mean, or do you want me to prove this? Closure with respect to addition and closure with respect to scalar multiplication. Does anybody want me to prove this? If yes, please speak out. Otherwise, I will leave this as a homework.
Sir, there's some subspaces we believe like a group of lines.
No, it could be group of lines. It could be just the origin, right? Any subspace. So just the origin, the set that contains only the origin, that also is a subspace. A
Right.
line passing through the origin is also a subspace. Plane also is a subspace. And it depends whether you are thinking of R2, R3, Rn, or in fact, even some of the examples of subspaces that we saw, right? So if I look at a set of all square integrable functions, then those functions which have a 0 DC value is also a subspace. We can take that subspace, right, and add it to some other subspace as well.
Okay. And sir, when we are saying this small u1, u2, we are adding all this. Do we mean that it is like if I consider u1, u2 all are lines,
No,
this
no,
side
no.
is
Oh, acha. So you are
just
saying
for
capital
example.
U1 to capital UN are lines.
Yes.
Okay.
Then when we are doing this sum of subspaces, do
Mhm.
we add all the lines and convert it into one another line which is equivalent to all this, or we just take group of all those lines?
No, see what this right hand side means is, so if U1 stood for denoted one line, say line 1, and UN stood for the nth line, right?
Yes.
This U1 is a point which lies on the line 1, and so on and so forth. UN is any point that lies on the nth line. Okay, so you have n vectors. These vectors are, I mean, the end points of that vectors are nothing but points on these lines. You add all these n vectors, you get one vector. That one vector will be an element in the resulting set. Similarly, now you're supposed to take all points on the corresponding n lines.
Okay, sir.
Okay, so maybe for as an example, so let's say this is the line that passes through. Just take these two lines for now. So this is the line that passes through the origin and the point 1, 1. And so this is L1. This is L2. L2 is a line that passes through the origin and the point 1, minus 1. Right? So what could be sum of these two subspaces?
The x-axis?
No. So let's see. So I have to take, so let's consider the point 1, 1 on line L1. Okay. This point has to be added to all points of the line L2. In that case, what will I end up with? I'll of course end up with this line, right? This line, isn't it? This line is nothing but L2 plus 1, 1. Do you agree, Krupal?
Yes, sir.
Right, now this is just for 1.11 on line L1, but you are also supposed to consider all points on the line L1. So now can you tell me what would be L1 plus L2?
So then it can be like a whole plane.
It has to be R2, the entire XY plane.
Yes.
Okay.
Yes, sir.
And if you want to consider a third line here, L1, L2 and some third line, for example, the x-axis itself, right? That also is a line. What would be L1 plus L2 plus L3?
So like it is also going to be like one of the line on this plane.
No, why would it be just one of the line?
Okay. Like sorry, means collection.
So basically all points, right?
Yes.
This also would be R2.
Yes, sir.
Okay, so don't, I mean, this diagram where I drew this blue line was just to quickly find out L1 plus L2. Okay, but don't think of L1 plus L2 as a collection of lines. You're going to basically get the entire XY plane.
Right, sir.
So can I leave the proof for this as a homework, or do you want me to derive this? Or do you want me to give more examples here? And I can do that as well. So can I leave the proof as a homework? All you have to do is consider, so for showing that this set, the sum of subspaces is closed with respect to vector addition, just take two elements from this set, right, and show that the addition of those two elements is also going to lie in the sum of subspaces. Is that okay, or do you want me to write the proof?
Sir, I guess we can do it now.
Great. Okay. Thank you. Just that we're sort of stretched for time a little bit, so that's why the simple proofs I hope to leave it to you guys. Okay. Right. So if I can write a vector v, right, as a sum of n elements, where each element comes from the corresponding subspaces. Okay. In that case, we write this n tuple of vectors and we say that this is a decomposition of the vector v. Okay, it's just a new terminology. Right? We can sort of decompose it into its constituent parts. You can sort of think of it that way. All right. Question then is this decomposition unique? In the sense that, let me elaborate the question. So if I say that W is the subspace which is the sum of these n subspaces, okay, so I'm fixing that the subspaces, the n subspaces. Okay, I'm not changing that. Now I'm taking some vector v in this subspace W. Right? Since the vector v belongs to this subspace W, it has to be true that I can write v as a sum of some n elements, right, where each of these come from the corresponding subspace ui. Okay, the question is, can I also write the same vector v as a sum of some n elements w1 to wn, where each wi again comes from the same subspaces ui? But at least one wi is not equal to the small ui. Right? That is what I mean by non-uniqueness. Is the question clear to everyone?
Yes, sir.
So what do you think? Will this decomposition be unique?
So it will depend on the subspaces we are considering.
Okay, so give me an example of some subspaces where the decomposition may not be unique.
So in the previous example that you took, for in this example only you can find a point. Suppose we find a point that suppose I
I don't think we can hear you clearly, Tarang.
Yes, sir. Suppose we take 3,2 point. 3,
Okay, so you're talking about this case, right? L1 plus L2.
L1 plus L2 plus L3.
Oh, this one.
Yes, sir. Suppose we take 0.3,2.
Okay, 3,
Then-
so 1, 2, 3. Okay. Go ahead.
Sir, then it can be written as 0, 0 plus 1, 1. Sorry, 0, 0 plus 2, 2 plus 1, 0.
Right. And
it can also be written as, sir, 1, 1.
oh, but this 2,2 is not a point on L2, right?
Sorry, sir. Change 2, 2 plus 0, 0. 2, 2 plus 0, 0.
No, once again. So what is the first decomposition?
2, 2 plus 0, 0 plus 1, 0.
Remember, the order is sort of fixed, right? So you cannot change the order. So 2,2 plus 0, 0 plus 1, 0. Fine. The other decomposition?
Sir, 3, 3 plus minus 1, minus 1 plus 1,
Plus
0.
1, 0. Good. Right? Is everybody okay with this? So the first part comes from L1. The first vector comes from L1. The second comes from L2. The third comes from L3. And you can see that for the same left-hand side resultant vector, I can have at least two. Of course, it is now easy to see, I hope, that there are infinitely many ways to write this, right? Out of which two are given over here. Is that all right? Does everybody see that this is not a unique decomposition?
Yes, sir.
Okay, how about this case? L1 plus L2 equal to R2.
Then it will be unique
Why?
because there are two coordinates only, so we can point at a we can make a point. Means plane have unique coordinates in every point.
So you think if I take two subspaces, then in this case it will always be unique?
If it makes R2, then two vectors are enough for
Okay, how
unique.
about this case? R2 plus line L1 is also R2, right? And R2 here can be seen as a subspace of V, which is
Yes.
R2 here. In this case, will it be unique?
No.
No, right? Do all of you agree to this? That the decomposition will not be unique in this case. But it will be unique in this case. L1 plus L2 equal to R2. Does it make sense? So we are interested in figuring out under what circumstances will the decomposition be unique and under what circumstances the decomposition will not be unique. Okay? So this example just sets the ground for that. And I don't know, it depends on whether you like signals and systems or not, but when you are sort of computing Fourier transform of a signal, you are exactly trying to do this. You're trying to decompose the signal into simpler elements. Right? I don't know where, I mean, do you want me not to mention signals and systems? Then I can do that. But when I've taught signals and systems, and I would teach exactly the same thing that I'm teaching you right now in that course as well, because you're doing the same thing. When you write a signal in terms of sines and cosines, right? You're just doing this. Okay, x coordinate plus y coordinate. Instead of these two coordinates, you will have infinitely many coordinates. That's all. And I don't know, you may have come across this Dirichlet conditions. Have you?
Yes, sir.
So as far as the signal satisfies those conditions, you know that the Fourier series is unique. So some ways, again, I'm trying to show that we are doing exactly the same thing, but in a much simpler form. Okay, in Fourier series, you need infinitely many terms. Here, you don't need infinitely many terms. Again, let me stay in my limit. Right. So, under what situation is the decomposition unique? Okay, because this is so important, so there is a new term that we give to the case where sum of subspaces, right, has a unique decomposition. Okay, and that is what is called direct sum of subspaces. Let me just read the definition first. In a vector space V with these n subspaces, let us say the sum of n subspaces gives you is denoted by the symbol capital W. Then we say that W is a direct sum of these subspaces if for every element of the sum of every element in the sum of subspaces small w, I can have a unique decomposition in terms of elements of these subspaces U1 to UN. Okay, and unique, by that I also mean that the order in which you write these elements is fixed. Okay, so don't think that since the group is abelian, so I can change the order and it would still give the same element. Yes, but here I am not allowed to change the order in which I add the subspaces. Right? So is the definition understood?
Yes, sir.
Okay. So now let us try to figure out under what situations or under what conditions is the sum of n subspaces going to be a direct sum of subspaces. Okay, and before we do that, just a small change in notation. So instead of writing just plus, you will now have a plus in a circle. Okay, so that is the small change in notation between sum of subspaces and direct sum of subspaces. Okay, so if I have a direct sum, then I will write it in this. Okay, so what is it that is required for a sum to be a direct sum? Okay, that is proposition 3. If I have n subspaces of the vector space V, then okay, V is equal to the direct sum of these n subspaces if and only if, okay, two conditions. Okay, since I'm writing the entire vector space as the sum of these n subspaces, of course, that is my first condition. Okay, that the entire vector space V has to be the sum of these n subspaces. That's the first condition. Second condition is the only representation of or decomposition. Sorry, I should write this as a decomposition, not a representation. the only way to decompose theta, right, as a sum of elements from these n subspaces is to use thetas that belong to each of these subspaces. Okay? If these two conditions are met, then the vector space V is said to be a direct sum of these n subspaces. So again, the second condition is special in the sense that if I can guarantee that the additive identity has a unique decomposition, then it's guaranteed that every other vector will also have a unique decomposition. Does it make sense? And by the way, when I say the thetas in UI, right, there is only one theta in V. Okay, it just so happens that each of the subspace must contain that theta, and so I can obviously write theta as theta plus theta, so on and so forth, plus theta. That should be the only way in which we can decompose the additive identity of the vector space. If that is true, and the first condition is true, then the vector space V is a direct sum of these n subspaces. Is the statement clear?
Yes, sir.
Okay, and let's quickly go through the proof. And of course, as you can see, this is an if and only if statement. So this way, of course, is easy. The sense that if V is a direct sum of these n subspaces, then what does it mean? What is the definition of this?
There is only one sum that contains.
No, and before that?
For every W in V.
So that's true, but first of all, this has to be true, right? Right? This is by definition again. Because remember, we have to prove that if this is the case, then 1 and 2 are true. So the definition of this assumption itself implies the first condition. And what does the second condition or second part of the definition of direct sum include? Says that for every W in V, I can write W as a sum of these n vectors, where each of the vectors come from the corresponding subspaces, and this is a unique decomposition. So if there is a unique decomposition for every vector in V, then theta also, since it is in V, must have a unique decomposition, right? So it has to have a unique decomposition, but what should be that unique decomposition?
The summation of all theta will always make theta.
Exactly. Since theta I already belong to UI, we know that. And theta 1 plus so on and so forth. Sorry for the use of notation here. Since theta belongs to each and every UI, and theta plus theta, so on and so forth, theta n times is theta, and therefore this decomposition of theta into n theta is unique. Okay. So this is half of the proof done. The more interesting part is, of course, this way. Right. So given that the conditions 1 and 2 are true, I have to show that V is a direct sum. How do I show that?
So by contradiction, we can assume that
Okay.
theta is made of n ways.
Why n ways?
We can make theta by n ways, or 2 ways are also.
No, but so that it is given to us that theta has a unique decomposition.
So we are assuming theta does not have unique decomposition.
Why? Wait,
Sir, we assume that a vector V in the sum of subspaces is having two representations,
exactly.
and we will prove that both representations are the same.
Right. Right. So let us say there is a vector V which have in the resultant vector space, right, has two decompositions. So V is V1 plus V2, so on and so forth, plus Vn, where each Vi comes from the corresponding Ui, and also that V is equal to W1 plus W2 plus Wn, where Wi is in Ui. Then if we subtract these two equations, what do we get?
Equal to theta.
Theta.
And since these are two different decompositions, at least one Vi minus Wi is not equal to theta, right? And therefore, theta does not have a unique decomposition. I think I forgot to make a note here that Vi minus Wi, of course, has to belong to Ui because of the subspace constraint. Therefore, this gives rise to a contradiction. So, P is a direct sum of these n subspaces. Is that okay? Any doubts here?
Sir,
Yes?
V1 minus W1 is equal to theta means they both are equal, right?
Yes.
Okay.
Right? Because, I mean, if V1 minus W1 is equal to theta, add the inverse of W1 or add W1 on both sides, you'll get V1 equal to theta plus W1. Theta is the additive identity, so theta plus W1 is W1. Implies V1 is equal to W1. Okay?
Yes, okay.
So this is a result for n subspaces to be a direct sum. If you have only two subspaces under consideration, right, then the conditions are sort of slightly simpler. Okay, the only condition is that the intersection of these two subspaces must be only theta. Okay. If I want to see if the vector space V is a direct sum of two subspaces U1 and U1 plus U2 or not, then I need to check these two conditions. Of course, U1, the sum of U1 and U2 must be V. So that is the same as condition 1 from proposition 3. Condition 2 simplifies to just seeing whether the intersection of these two subspaces is theta or not. Okay, so this proposition is something that you will work out in the next tutorial. I think the next tutorial is 9, right? I've been mistakenly calling it tutorial 3 for some reason. 9 or 10, I don't even know. Not. Okay, so you'll think of this case on Saturday. Let me give you examples of direct sum of subspaces. Okay, so, and I'm more or less certain you have seen them. So first example is, let V be the vector space of all real valued functions defined on R, okay, over the field R. All right. UE, right? The subspace that I'm going to consider, I'm denoting it by UE, and you will see why UE makes sense. The set of all functions in the vector space V such that f of minus t is equal to f of t for all real t's. What is this set?
Set of even functions.
Exactly, set of even functions. And what I did not prove, but I'm assuming, is that this is not just a set, it is a subspace. Okay, so maybe can you quickly verify and convince yourselves that this set is actually a subspace? Similarly, UO going to be the set of all odd functions. Again, try to convince yourself that this is not just a set, but it is a subspace. Are you all convinced that these are not subsets? I mean, not just subsets, but they are subspaces?
Yes, sir.
Okay. What is the intersection of these two?
Identity.
Now, in this particular example, what would be that identity?
0.
The zero? I mean, what do you mean by zero?
F equal to 0.
Yes, the zero function. Okay. So I'll write it as theta, but I'm also going to define this. Theta t is equal to 0 for every real number t. Okay, that is what I mean by the additive identity here. And what is UE sum UO?
Theta.
No. How can it be theta? UE intersection UO is theta. Why should the sum of these two be theta?
R equal to V.
Yes, it is V.
Is V. Why? How?
Sir, because every function is either odd or even or not,
or their same.
or a sum of odd and even function.
So how do you prove that? I mean, you can't state it directly, right?
Like
And
that.
I think you have seen this somewhere, I'm sure. F of t
Yes.
Yes.
plus f of
Minus t.
Minus t.
right? So you can see that this is the even part. And this is the odd part. Right? So ft is fet plus fot. Right? So we have basically, if all of you, I hope this is not too difficult to see why, but we have basically proven this, that the sum of UE and UO is equal to B. And we have just shown that the intersection of these two has to be theta. Again, I just directly wrote this assuming you can prove this. Okay, but remember, you should prove this, that the only function which is both even and odd is the zero function. And I hope you don't find it very difficult to show that. Once both of these you've been able to show from proposition 4, what we have, or what we can show basically is that the vector space of all real valued function is a direct sum of the subspace of even function and the subspace of odd functions. Is that okay? Any questions in this example? Yes or no? You want time to go through this example? We can pause for a couple of minutes. Is this fine?
Yes, sir.
Right. I think there are a couple of more examples. With that, I will leave it in the for the tutorial. Okay. I hope the basic idea behind direct sum is clear. So now let's talk about something that we have already done as far as Rn is concerned, the vector space Rn. Okay, let us now define what is meant by span and what is meant by linear independence. Okay, so let's first start with span. Okay, so let us start with an arbitrary vector space V, and let us start with a subset U that contains n elements from the vector space V. Okay, then we can define span of this set U, okay, to be the set of all possible linear combinations of elements from U. Okay, I hope the definition is not too difficult to understand. Set of all possible linear combinations of elements from U. Right? Is clear? Should be.
Yes.
Okay. There's one major problem here. And this again sort of fortunately or unfortunately ties this to your signals and systems course. So we have defined span of a subset U, assuming it has n elements, right? But in a vector space, you can also have subsets that may have infinitely many elements, right? I mean, typical example would be, let's say the vector space is R2, and I can in principle sort of take the subset of all points that lie on the x-axis. That, of course, is an infinite set. How do I define span of a set that contains infinite number of vectors? Is the question understood?
So, but why there will be a problem if the cardinality is infinite? Because
Exactly.
we can
Yes.
define it as the linear combination of all the points.
All points. How? How do I define? So there is, let's say, V1 to, let's say, I mean, just assume a slightly simple case where k is an integer, right? What does it mean for something like this? Can I define what this means? So A1 V1 plus A2 V2, so on and so forth. Right? It never stops, right? Does the vector space have enough tools available with it to define this? See, what is a vector space? Is V with
Vector addition and vector multiplication.
no and scalar multiplication, right?
Oh, yes, scalar multiplication.
What is vector addition? It's a binary operation, right? V cross V to V. Scalar multiplication, again binary, F cross V to V. So using this binary operation, I can define a operation that operates on three vectors, right? You first combine the two, then combine the resultant with the third. Right? So
Yes, sir.
you can extend it to three vectors, you can extend it to four vectors, you can extend it so on and so forth to n vectors. Can you really extend it to infinite vectors?
No, sir.
Right? So that is the issue over here. This
So-
is undefined. In a vector space.
Yes, sir, because we do not know the result of n minus 1 operations because n is infinite.
Exactly. If that is not defined. It's not that we don't know. It's not even defined. We don't have the tools to sort of do that. So it's like saying, can human beings fly? Can human beings fly to a height of 500 meters without anything? You can't say because they can't fly to 400 meters, so they can't fly to 500 meters. Like basically, we cannot fly. So that's the situation here. This is undefined. This operation is undefined. The vector space structure does not have the tools for this to be defined. Kandar, do you have a question here?
No, sir. I was thinking that maybe in the example that you gave about the x-axis, the points on x-axis, so we can just take a single point 1 comma 0 and by different AIs we can get the whole. So basically we can reduce the span to some maybe some finite elements of u.
Agree. But now again, unfortunately, I have to give you an example in your signals and systems course. What do you do in a Fourier series?
So it is a weighted sum of signals with all the frequencies.
All frequencies. How many frequencies are there?
Infinite.
Infinite. Right? So there it's not like all points are on the x-axis. You really do need each and every of the infinite frequencies for some signals, right? For example, square wave, right?
Yes, sir.
So there you cannot even reduce this. Okay, so in principle, as of now, Fourier series is not possible for vector spaces, at least those vector spaces that we have dealt with till now. Okay, so what we can do over here is we can have a sort of a compromise. Okay, so if there are infinite elements, right, in my set U, I will define the span of U as the set of all possible linear combinations of all finite subsets of U. That is how I will define the span now. Right? The problem is, as soon as I have infinite vectors, I cannot define a linear combination of those elements. But I can surely consider all finite subsets of U. Okay? Once I have a finite subset, defining span is no problem. Right? That I have already defined. So collect all spans of all finite subsets of U together. That is how I'm defining span of a set which has infinite elements. Does it make sense?
But sir, there will be finite subsets.
Yes. So, but you're basically taking union of infinite sets, right?
Yes, sir. Means we are not operating among the finite subsets.
Yes, there is no vector space operation performed on infinite elements.
Means an element of one finite subset is not operated with an element of the other finite subset. Means It is not
No, 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 no. See, since it is all finite subsets, so for example, let us take the same case where U is having infinite elements which are indexed by positive integers. Okay. One finite subset of U, I'm going to denote it as U1, which is, let's say, just V1, right? This is a finite subset of U.
Yes, sir.
Yes. So, and therefore I have no problems in defining span of U1, right?
Yes, sir.
Right. Then take U2 to be V1, V2. This is also a finite subset.
Yes, sir.
So I can define span U2. So similarly, right, have as many all, right, which is why I wrote this in bold, all finite subsets. It doesn't matter whether some elements have already been covered in some other finite subset or not, right? All finite subsets. So for example, V3, V100, V200 is also a finite subset of U, right? So take that as well. Take union of all of these.
Yes, that means my question was, sir, that we are not linearly combining that subsets. We are just taking in the union.
Union, exactly.
Yes, sir. Yes. Understood, sir.
Okay. So as an example, if I take these polynomials, right, 1x, x squared, x cubed, so on and so forth, right? There is no, I mean, this is an infinite set, right? What would be the span of this?
All possible polynomials in
Exactly.
single variable.
Yes. So I don't know. Have I introduced this notation?
Yes, sir.
Right. So this would be P of R, basically. Okay. And I think I'll stop after I discuss this last point here. So given any set U, or given any subset U of a vector space V, will span of U be a subspace of V?
Yes, sir.
And can we prove this?
Yes, sir. It have linear combination of all element of V, so it will
No,
be
not all element of V, of U.
U. Yes, yes. So it will be close under addition and multiplication, because if we take scalars of 1 1 1, so we have addition of all elements.
Right. So in general, the proof strategy, if you want to prove any set is a subspace, just pick two arbitrary elements, right? V and W be in span of U. What does it mean for an element to be in the span of some subset U?
If U contains element U1 and U2, then V is equal to A U1 plus B A1 U1 plus E2 U2 up to
Let's
A and
just
UN. Yes,
exactly A and UN. How about W?
B1 U1 plus up
No,
to
why U1 to UN?
Because it is span of U, so uh, it should contain linear combination of elements of U.
Yes, but should V and W be given as the linear combination of same n elements? It could be some
No.
different M elements also, right?
Yes, yes, sir.
As far as those elements come from you, I don't care. Okay, now what can we say about V plus W? That, of course, I think now it's straightforward. Right? So again, I
Also,
think, right. So intuitively, I sort of know that you all agree that this is a subspace. But I just wanted to point this thing out. Be careful when you actually write the proofs. Okay, so don't make any assumption which is not given in the statement, right? So for example, why should we assume that V is also a linear combination of U1 to UN and W also is a linear combination? Probably a different linear combination, but still a linear combination of the same elements, right? Do not make such assumptions. Since V plus W is this, of course, this belongs to span of U. Okay, and similarly, you can show that the span of a subset U is closed with respect to scalar multiplication as well. All right, so therefore, span of U is span of U has to be a surface of V. Okay, so we'll stop here for today. The next class, we will look at linear independence. Right, and that, of course, we have seen it in the limited context of Rn already when we were looking at matrices. Now we'll define linear independence over any arbitrary vector space. Okay, so for example, you will be able to talk of linear independence of sine t and cos t, which is what you have been using in your signals and systems course. Okay, so thank you and see you guys on Tuesday. Also on Saturday in the tutorial.
Sir,
Yes?
sir, I had a doubt in the project question.
Okay.